Hi, I'm Will, and this is my fifth and final Physics 1 lab report. For my lab 5, I decided I wanted to create a model for inelastic collisions in GlowScript. I stuck with perfectly inelastic collisions as they allow me to calculate the final velocity of the additive object from only knowing the initial velocities and their masses, and I decided to model collisions between my own car, a minivan, and my sister's sedan, as I thought it would be interesting to see how the high mass of my minivan compares to the lower mass of my sister's sedan, and also just seemed kind of funny. So, although I have no observations of our cars colliding for obvious reasons, I can use real data to develop scenarios and then model them in GlowScript. And my goal is to create a thorough model that maintains conservation of momentum while allowing kinetic energy to fluctuate accurately, representing an inelastic collision. I succeeded in this goal and will explain later. Next, I would like to talk about the physics behind the lab. The most important physics principle in this lab is conservation of momentum. It was key to modeling how the cars interact post-collision. Because the collisions were perfectly inelastic, I made sure their masses added and had a single velocity post-collision. I also used the energy principle, and more specifically the kinetic energy formula, to find out how the kinetic energy changed after the collision. And I also used Newton's second law when modeling the objects and how they move through space. The velocity and position update formulas were essential for this. Now I'd like to go over my GlowScript model. Before I show the actual code, I wanted to run through my process so it is easier to understand. Firstly, the model starts with two objects, each with their own initial velocity and mass. Because it is a collision, we don't look at outside forces, and those are ignored, and we stick to the initial velocity for the purposes of this lab. The two objects then run through a standard position update loop, very similar to previous labs, and at the end of this loop, there's a break that triggers if the objects come into contact, where contact is defined as the radii of the two objects touching. Upon contact, a new object is created to represent the collision and the sticking of the masses together, and then that object runs through the position update loop with its new mass, which is the addition of the first two, and then the velocity is calculated via the conservation of momentum formula. The model also calculates the initial and final momentums as well as the kinetic energies for easy comparison. Here's the actual GlowScript code as well as the link if you'd like to look at it. Um, and now I'd like to quickly run through the two scenarios and how they are modeled. Firstly, I modeled a head-on collision between my car and my sister's. This is scenario one. In this case, the system is the two cars while the surroundings are negligible because once again it is a collision, so the forces they add are essentially zero in comparison to everything else. So in this scenario, if I were driving at 60 miles per hour and she were driving at 40 miles per hour directly at each other and we were to collide in a perfectly inelastic collision, what would happen? And my GlowScript model allowed me to find that out. So given that the van has both a larger mass and velocity, um, and the objects were moving in opposite direction of each other and toward at each other, they continued to move in the direction of the van because of its higher momentum. Even after collision, they continue to move in that direction, which is shown by the red ball here, where the green is the van and the blue is the sedan. The speed at the van was reduced to about 11 meters a second, or roughly 24 miles per hour. And just a reminder, it started at 60 miles per hour. In the second scenario, I really wanted to test out more of my glow script, so I had them come at different angles. It was a bit tricky to get them to line up to hit each other, so I ended up doing it at 90-degree angles. But once again, the system in this situation is the two cars and with negligible surroundings. And here you can see the van and sedan collide at a 90-degree angle, and the model succeeded in modeling the collision and sent the additive object, the masses together, off at an angle from the collision. Both scenarios maintained momentum as shown in both the slides, and there was differences in kinetic energy in both cases. And in both cases, it became smaller, which I'll discuss now. So, before concluding, I want to discuss why the kinetic energy gets smaller as well as potential sources of error. Firstly, why does kinetic energy get smaller post-collision? So unlike elastic collisions where total kinetic energy is not where total kinetic energy is preserved, oftentimes in perfectly inelastic collision, kinetic energy is lost via the compression of the objects around each other, causing them to stick. And in a car wreck, this definitely contributes to it, as well as the loss of energy through things like vibrational, which would be sound probably, and thermal, so like heat escaping from the collision. And then finally, I just want to briefly go over some potential errors or sources of errors and the difference between this and the real world. So one key thing that would separate the models from real world fiction, in this scenario, we regarded friction as negligible, which would change the speed and velocity. And then also another thing would be that we said there was no force acting on it, when in reality, cars don't really move at a constant speed. So if they're speeding up or slowing down, that would change things and potentially cause a different answer. Thank you for listening.